What's up, everybody? This is Matt Brown with another IoT hacking video. Today we're taking another look at the Mojo C-75 Wi-Fi router, and we are going to continue on our adventure with this device. Last video we extracted the firmware off of two flash chips that were located on this device, and now we are going to attempt a firmware modification in order to get a root shell. If you recall from the last video, there is this limited config shell that is restricted. It doesn't give you full shell access to the system, and we would like full root access to this device. So we are going to accomplish that today, hopefully. So let's go over to the desk and just remind ourselves where we left off and some things I've done since the last video. So you'll see one chip has been returned to the board. That is the chip that has the primary 5 file systems that has the bootloader, the kernel, the root file systems, and some other partitions. And then still not attached to the board, I have that other chip that held that writable partition, the OPT partition. And so what we're going to do, and if you remember from last video, it's this chip that contained the shadow file where the root password hash was. That hash, I do believe, after doing some reverse engineering, is not going to be crackable. I believe that is completely randomly set on firmware update or factory reset. So we are going to need to write our own password hash to this flash chip. So let's go back over to our computer and just jog our memory with where we left off on the firmware extraction side. So we will remember that, I'll make this a little bigger, that we had these two different flash chips on this device. That's kind of unique. Most IoT devices I pull apart just has one flash chip that's big enough to store all the partitions on. This one has two. And if we remember this U5, I've labeled them U5 and U8 just because on the board, that is how they're denoted on the PCB. And so that just helps me keep those from getting mixed up in my head. So this U5 is that first main flash chip that has bootloader, the kernel, and the root file system, and this U8 firmware file is what we extracted off of that other chip that has the OPT partition. And we'll just jog our memory here as we start to modify this firmware. So this is what we want to modify. We want to create a new bin file that we can then program, that we can write back to the flash chip that contains a file system that inside of it is the shadow file with a password hash that we control. And so we are going to do that now. So we're going to make a directory. We'll just call it firmware mod, and then we're just gonna make a copy of this. I just like to always keep a copy that's safe and untouched, right? Because you never know when you accidentally blow away your firmware file and then you brick a device and you never have that firmware ever again, and that's not a good situation. So we're just going to copy it into that directory, and then we're going to hop in there. Now, if you remember, we used the Jefferson command instead of binwalk because binwalk detected a bunch of extra stuff and tried to pull out the JFFS2 file system like 5 different times, and it's a mess. So Jefferson is actually what binwalk uses under the hood to perform that extraction, and so we're just going to directly call that because we know, oh yeah, so let's show first, because we know that this is just a JFFS2 file system because there's only one partition. There's not a bunch of different partitions on this disk, and so we can just run this directly, not at some offset inside this binary. It gives us some warning about something being depreciated. We don't really care because now we have the root file system. And if you recall, inside of here there are a bunch of files, and the one that we care about is this shadow file, right? And there are these password hashes, and I'm not going to go into it all now, but I believe firmly that this root and the support user password hash are set in a completely random way that no one will ever be able to log into those accounts as is, if I am correct in my understanding. But we can modify this file and create and put in a password hash that we know. So right here in the shadow file, you see it starts with a $1. That 1 is denoting the algorithm that is being used for the password hash. So we can actually go ahead and use OpenSSL's password program, and we can do -1. That corresponds to this -1 algorithm, which I believe the name of that is called it's like MD5 crypt, or sometimes it's just referred to as crypt, the crypt function. And so we are going to run that program, and then it's going to just prompt me for a password that it wants me to create a hash for. So I'm going to just put in the password root. So my password on my device will be root. If you ever get physical access to it, you'll be able to own it. All right. So you'll see that it output something very similar to the password hash that's inside that shadow file. And notice that it's separated by the $. So what's inside the first location there inside the $signs is the hash type, and then the second part of that is a salt. And so this is a salted password hash, and then at the end you have the actual hash value. So all we need to do is take our new password hash, and we're going to go ahead and edit this shadow file, and we're just going to remove only the hash section. We're going to leave everything else the same, and we're going to paste in our password hash that we know the password to. So now we can back out of there. So now this directory, now we want to turn this directory back into a new binary firmware file. And so what we're going to do is we're going to use the make fsjssf2 command to make a new file system. Now, there are a bunch of options here. We're not going to go over all those, but I want to point out a couple of them that tripped me up along the way. I'm gonna talk about some of the things that I had that failed along the way to getting this device, this firmware right to succeed, right? So where is it? Okay, so I want to talk about that second. Okay, so there is a flag right here for big endian. So the JFFS2 file system, that's a mouthful. It can be little endian or big endian. I'm not going to explain too much, but it has to do with byte ordering within multi-byte data structures on computers. And so we just want this to match what this other file system that we extracted. Well, if you remember, when we ran this file command, it not only told us what file system type it was, it said that it is big endian. And this is really important because by default, this command to make a file system, it defaults to little endian. So we do have to put that -b flag in there. Now, you'll notice in my notes, I'm explaining what didn't work. So I, like many of you, when I don't know how to do something, like creating this file system, I go and I Google something and I try that command and I see if it works, right? So the example that I was given had this parameter set. And so let's go back to that help. We can actually scroll up to the -E option and look at what that is specifying. That is specifying the erase block size. And it says that it defaults to 64 kilobytes. But I was given this example of this command where it manually specified a different erase block size. Well, so I do a little research on this erase block stuff, and I can't quite figure out what it is, so I just blindly try this command. Well, the long story short is after I solder that chip back onto the board, I boot the device up, I get this error, and the device just boot loops eventually. It says, you know, perhaps the file system was created with the wrong erase block size. Well, that was very helpful that it gave that verbose of an error message. So I knew exactly what was wrong with my firmware build. And then I went back to researching what this erase block is. And so what this erase block size is that certain flash chips, they can't just do an operation. If you're doing an erase operation, this is different than a write operation. This is different than writing a bunch of zeros to a certain section of memory. If you want to do an erase operation, there is a minimum size that it can do those erase operations in. It's meant to do, you know, to erase a large section of the flash chip at once. And so it needs to know this value. So I went and I looked at the data sheet. So this is the data sheet that corresponds to that flash chip. Macronix is actually they're better about this. You can see up in my URL. This is like hosted on their site. They provide this freely. They don't make you sign up for an account. I really respect that. So I went in this document, and again, I'm really new to this whole concept of an erase block. So what am I going to do? I'm just going to search for the word erase, and then I found right here this block erase operation described for this chip, and zoom back in for you. And right here, it said that the instruction is used for a 64 kilobyte block erase operation. So I'm like, oh, cool. So that's what I need to use, which means that I don't even need to manually specify a parameter, because if you remember, that is the default. So all I had to do to get this to work is I just had to not specify this -e flag. So, so let's go ahead and make our file system out of our modified root directory here. So again, we're doing -B for big endian, and then -R just shows where the thing is that we want to package up into a file system, and then -O is going to write out the file. I'm not going to call it, you know, modded firmware 2. I'm just going to call it firmware mod, because we know that this is correct. So that goes and does that. And now we can run file on firmware mod, and we can see that it is a big endian JFFS2 file system. So that's great. Now, something that I was worried about, but then it made sense and I wasn't worried about it, is that the size is very different between my firmware modification and this binary. And that's because inside this binary, if we go to the end of it, you will see that it is just a bunch of blank data, right? So that file system doesn't take up the whole 16 meg that is available on the chip. So because of that, it just has, when you read the firmware out, it gives you every part of the flash chip when you use that reader, right? Even if it's blank, it'll just give you all Fs or all zeros, right? Depending on what erased is on that firmware chip. So, so at first I was like, oh, it's like, why is my file system so small? And then I'm like, okay, that's why. And I just stopped worrying about it and gave it a chance. So now we have our firmware file here. And so all we're going to do, you saw that we have the chip in the reader. Not there. All right. So we're going to go here, no programmer found. Let's turn on our programmer, and then it flashes up, and cool. Okay, so it recognizes that we have the programmer connected now. So the first thing I'm going to do is I'm going to perform, let's just perform a read operation really fast. Oh, so one thing, yeah, the XGecu reader, you just run into bugs, and you learn to just expect bugs, and then you try to work around it. So one thing I noticed is that this SPI clock frequency defaulted, I think, up here to 25 megahertz, and that was giving me all sorts of problems. So I backed it down to 16, And it seems like that's the sweet spot, but I will still run into errors. We will probably run into errors while recording this video. So the first thing I want to do is I just want to do a read operation. I'll just read the firmware off the chip again. It just reads it into memory in the program. It doesn't actually save it anywhere. But let's just make sure we're communicating with the chip just fine. Okay, the read worked. That's good. So now what I need to do is I need to do a load. I'm going to do a load operation here. And I'm going to put the path. And you notice this is like a weird, like, this is how Wine accesses like the Linux file system. So it's a very weird path here, but I'm loading that binary that we just created into the memory space over here. Oh, I forgot. No, we're gonna do something else first. So I've found that it was very helpful to do this erase operation, and this is the thing that's gonna fail. So okay, I'm going to first erase the flash chip. And so that will help out with a number of issues that, that may arise, but it's just a good idea before you program to do an erase. And you'll even see here in the options for programming, it'll say, there's this option that I have unchecked that says erase before. And the reason that I don't do that is because this erase operation in XGecu says that it failed. You notice here it just hung up, and then if I try to do another operation without like power cycling the programmer, it'll freak out at me. So now, okay, it said our erase operation failed, right? But if I go and I do another read, we should see, hopefully, that it actually did perform the erase operation just fine. This software just says that it failed. So, okay, there we go. And then if we don't want to scroll down and inspect every byte inside of here, we can do a blank check. And it will check and it will ensure that every byte is FF on this flash chip. So, and it passed. Cool, device is blank. Thank you very much. Even though it told us the erase operation failed. So now what we're gonna do is now we're gonna load. Okay, so now we're gonna run this load again and load our firmware file from our computer into the software, right? So now it is queued up. And so now we can go and we can run program. And this is really 50-50 chance whether this is just gonna succeed the first time or whether we have to flash it a couple times to get the verification to work afterwards. It's just random. Some of the variables might be how well I've cleaned the chip and how good of a connection it has to the reader. And I do believe that's why it tells you that reducing the clock frequency, especially if you're using like a clip or something like that, it can increase your chances of success. But okay, so it succeeded with the program, but now it's going to verify. Now it's going to go and basically verify. Hey, look at that. It worked the first time. That like never happens. Okay. So now our firmware has been written. And so now if we want to be extra sure before we go through all the effort of resoldering that chip back on the board, we can do yet another read operation. And what we're going to do is we're going to take that file and we're going to save it. Oh my gosh. Well, it encountered an error. That's awesome. You know what? Screw it. We are not going to perform the check. So all I was going to do is I was going to go and I was going to reread the firmware and I was going to compare it with our firmware mod. But honestly, that would be complicated because I would have to like DD off the second half of the firmware that I just read back because it would have all those Fs at the end. So that just is something you can do to verify things. But we're just going to go for it, you know? Okay, so let's go back to our desk. And so we are going to prep this surface here. We will actually go underneath the microscope and show our spot here. I am going to get some gloves on because I do not want to get flux all over my hands. I've done that too many times. So what we're going to do is we are going to clean this old solder off of here. And then we're going to replace it with some fresh solder. And I already have some flux down here, but I'm just going to put a fresh bit of flux there. And I'm going to turn on my air extraction. So that's going to be the annoying noise that you hear now. So I'm just going to press down. Oops. If you notice that fail, I just knocked this little resistor out of the way. That was not cool. All right. Well, we're going to fix that. You know what? We're going to fix it with some hot air is what we're going to do. I'm worried I took all the solder away from it, but there might be a little left just to let me like move it back onto its spot. Come on. Oops. Go back to your home. Okay, there we go. Yeah, that does need a little more solder. Wow. That is like a C- grade solder job there, but you know what? It'll work. Okay, now let's go back to clearing this stuff off. Carefully. You should be careful. Okay, and well, that's new solder over there. Don't need to clear that off. All right, so now I've got flux on here, so we are just going to drag solder across. Okay, need a little more flux. It's not working as easily as it should. There we go. More flux. And whoa. Right. Gonna clean that iron off a little bit. There we go. All right, we are. Come on, man. All right, we are ready to put our chip back on. So, take the chip out of the reader, and we are going to remember to put it the right way. So we have a pin 1 indicator up here on the board. Oh man, you guys got a reflection there. Okay, there you go. You see it there. So pin 1 onto the chip. And we'll just try to get it in a good starting location, and now we're going to throw some hot air at it. And we'll keep an eye on those resistors. Hopefully they don't blow away. Oh, I almost forgot. Okay. I'm going to show you guys something that happened. Okay. So, see that the chip is obviously not on the board. I almost forgot to show you this failure condition that I hit. Okay, let's go back to my screen really fast. Okay, so I'm going to open up that shell on the device and get it ready. This has our RS-232 cable connected to it. Okay, it's ready. And so I have the one chip connected. I have the other chip completely removed, right? Let's watch what happens. So that when I was working on this, I spent hours thinking that my firmware modification was not working properly. But it turns out that I just didn't have the second chip properly placed on the board. I just threw hot air on it really fast. It didn't have a good connection, and it could not read the chip. And so I thought it was something to do with my firmware modification, right? But you can see here that like all of the bootloader, the kernel, the root file system are on that other chip. They were connected just fine. And so the system almost acts as if it's going to work fine. And then I got this error right here. I said, okay, so cowardly refusing to erase blocks on file system with no valid JFFS2 nodes. Okay, so, and I was viewing this as like, I'm like, okay, it's not working, right? You know what I didn't have last time? I did not experience this last time. It's still telling me that I can maybe log in, right? Like that chip is not connected to the board. Will config work, that login? No, it won't. It won't, right? Like the shadow file literally like doesn't exist, right? Before it was just boot looping on me, but it would give me this error, and I assumed that I was doing that make fs jfffs2 command wrong. I was messing up something. I was missing something. I was working on figuring out the endianness and that erase block size, and I thought I still had some other problem with my firmware mod, when really I just didn't have the chip properly connected to the board. But the system would still like mostly work, but it obviously wasn't recognizing my modification here. So, because that other chip, it just couldn't read it. It just couldn't read it at all. It's not that there was a little problem with the file system that was wrong. So we're gonna turn that back off, and we're going to now resume our reattachment of this chip. Just wanted to share that with you because sometimes you can think that you're doing something very technically wrong, right? Some really complex problem, but sometimes the most simple things are the things that will mess up your life for hours. All right. And now I've got shaky hands, wow. All right, let's go slowly into place. And then I'm gonna press down on it, and I'm just gonna give it time. It's like we talked about, we want this chip to be fully seated onto there. All right, that looks good. And I'm even, because I've been paranoid from that past experience, so I'm pressing down with my tweezers, not really hard, but just very gently until I know that solder has turned cold. Now I can put that up there. All right, now we are ready. We're ready to try again. So we'll, wisdom would tell us to wait and let that chip cool down a little bit, but we're not going to do that. All right. So here is the boot process. And it's also like super scary because it does take it just a little bit of time to drop into the console where you can actually start to interact with it. So that also is potentially makes you worry about things. All right. But it looks like a much better, this looks like a good solder job. Let's hope. Yeah, this is the part where it just sits here and making you nervous for like 45 seconds. All right. For some reason, I think this is a good sign because in the past, when that firmware mod failed, that sometimes would say failed. Not necessarily all the time, but it definitely sometimes said that check failed. Oh, and a funny thing, in reversing some of the firmware, this is good that this is off, because if FIPS mode is on, what it does, I believe on boot, it's either on boot or on just on factory reset, it'll completely disable. It'll run password-L to disable the root user. So even if you knew the password to it, you wouldn't be able to log in, but that is off. All right, the moment of truth. Root. We're in. And you'll remember that this system is kind of weird, that all of these users, all three of these users are UID 0, which, if you're not familiar with that, in the Linux world, the root user can be renamed to all sorts of other things, but it's really this user ID 0 that's denoted here in this file and up here in the ID command. That really is the thing that means that you are the super user that can override any type of permissions in a discretionary access kind of way. So there we go. We have a full root shell to this device, and now we can start to use that shell to perform other security research and just have full access to this system. This was a really fun project. This is the first time that I have ever done a firmware modification via chip off with that JSFS, that file system type. Yeah, I can't even say it. So thank you everybody for watching this video. Please like, comment, and subscribe. Tell me if you enjoyed this content. I think there's definitely one more video coming about this device. I didn't expect there to be, but there are some interesting things that I have found in the network traffic. So, got nothing else for you. Have a good day.